Hello again. As suggested earlier, formulating the information on the reactor's inflow and outflow loads and the reaction rates into a mass balance analysis allows one to determine the reactor's size and to predict its performance. In the next slides, I will discuss constructed wetlands as a significant on-site treatment solution and demonstrate how to estimate the area required for such systems. Constructed wetlands are unique, low-cost, low-tech engineered systems. They are designed and constructed to mimic and utilize the natural functions of wetlands vegetation, soils, and their microbial population to treat polluted water. The main process is the biochemical degradation of pollutants in the filter bed's biofilm. Constructed wetland bed typically contains different types of filtering material, usually sand or gravel. There are two major constructed wetland designs. One is called free water surface, with plants such as seen in the photo, and the second is known as subsurface flow systems. Free water surface constructed wetlands are shallow ponds, typically less than 1 meter deep, but they are less efficient in treating water and require large area. The pond bottom contains substrate that supports rooted plants, such as rushes, but other floating or submerged plants are also used for water treatment in a process called phytoremediation. These wetlands often resemble natural flood areas or swamps. Yet, they are quite inefficient in water treatment per unit area. Thus, they are beyond the scope of this course. Subsurface flow constructed wetlands are more abundant and have two main designs: horizontal flow, as seen here, and vertical flow, as will be shortly discussed. Typically, an on-site horizontal flow wetland has length to width ratio of around 0.6 and is about 0.6 up to 1 meter deep. In this wetland, water enters via high porosity inlet zone, where the larger suspended material is dropped. The second stage contains more fine gravel or sand media, where most of the microbial activity takes place. This activity can be aerobic and/or anaerobic. While the role played by plants in these systems is still controversial, they are mostly considered to contribute to the water treatment through assimilation of pollutants, gas exchange, enhanced microbial activity near the root zone, and through moderating the water flow and temperature. The plants are also aesthetically pleasing and may reduce bad odors from the wetlands. The water exits the system via an outlet zone, which contains larger porous media. Here we can see the major steps involved in establishing a constructed wetland. Initially, the pond with a 1% slope is excavated and lined with polyethylene sheets, ensuring that there is no pollutants leaching into the groundwater. Ventilation pipes that allows aeration of the wetland's bottom are introduced, after which the wetland is covered by the filter bed materials. Finally, various water plants, such as rushes, typha, and others, are planted in the bed. In summary, in constructed wetlands, wastewater moves horizontally for 2 to 6 days through the gravel and underneath the surface. The predominant treatment mechanism are physical filtration, sedimentation, and biological degradation. So how do we actually approximate the area required for a horizontal subsurface constructed wetland? Let's, for example, estimate the area needed for an on-site wetland to remove BOD to the regulatory levels, assuming a 5-person family that produces 0.15 cubic meter per person per day with an inlet C0 concentration of 100 milligram per liter. The regulation suggests that 10 milligram per liter BOD is required before the treated water can be reused for irrigation. Thus, the effluent concentration CT should equal 10 milligram per liter. Based on the literature, the reaction rate for BOD removal is 0.1 meter per day. Let me just tell you that if you correctly use the equation on the slide, the estimated area would be 17.3 square meters, and I suggest that you check it yourself. In a vertical flow constructed wetland, the water is distributed over the bed surface area and flows vertically from the top of the bed to the wetland's bottom, as can be seen by the arrows on the slide. The treated water is then drained by perforated pipes towards the wetland outlet. Distributing the water typically requires the use of pump, whereas in the horizontal flow wetland that we have just discussed, gravity flow is sufficient. Unlike the saturated flow in the horizontal flow constructed wetland, the flow here is typically unsaturated, so the water is more aerated. The latter enhances the water quality and the overall wetland's efficiency to degrade organic matter at much shorter hydraulic retention time. Therefore, the dimensions of vertical flow wetlands are significantly smaller than those of horizontal flow ones. In the vertical flow constructed wetland, ammonia oxidation is efficient, but removal of nitrogen via denitrification is less efficient. Here you can see an example of an on-site vertical flow system in a small farm, treating about 6 cubic meters of farm wastewater per day. It can be seen that the wetland is divided into 2 beds, or compartments. Each bed operates for several days, after which the water is diverted to the other bed. The resting bed is better aerated during this period, and absorbed compounds are further degraded. This staggered operation significantly enhances the system's efficiency. While reactor models are based on mass balance analysis, often small-scale reactors are designed based on a rule of thumb and the practical experience, such as in the following example for the design of vertical flow wetlands in temperate or warm regions. Let us use the same example of the horizontal flow constructed wetland and see the required dimensions. As you may remember, we assumed a 5-person family that produces 0.15 cubic meter per person per day, with an inlet concentration of 100 milligram per liter and an outlet concentration of 10 milligram per liter. Going through the calculation, the estimated area for the vertical flow constructed wetland is 2.25 square meter, significantly smaller than the horizontal flow one. As you can also see, the bed filter structure is a bit different than in the horizontal flow wetland, but the principles are the same, and the bed is used to treat the wastewater by physical, chemical, and biological mechanisms. Before we move on, I just wanted to remind you all that constructed wetlands were given as an example, but there are several other solutions, such as rotating biological contactors, or RBC, moving bed bioreactors, and others. Yet, these are beyond the scope of this course.